Okay, we're gonna get started. Didn't want to keep people here all afternoon. Thank you and welcome for coming to the 2025 Geophysics Field Camp final presentations for the community. I'm Matt Siegfried. For those that don't know me, I'm the associate professor in the Department of Geophysics and the field camp director. Neither my co-director this year, Dwight Milstein, nor the regular co-director Brandon Dugan could be here today, nor is our department head Paul Sava. They are strewn all over the world now. I know Brandon is online right now from the middle of the Atlantic Ocean on a drill rig. So that's how dedicated he is to our field camp. So I'm going to do a quick intro. I'm just going to throw it to the students as quickly as possible, but I wanted to give you some context for what you're going to see here, if this works. And it doesn't. They updated these computers and they don't work that well, as it turns out. But our story here starts almost 99 years ago. This is from the December 1926 Bulletin of the American Association of Petroleum Geologists, volume 10, number 12, Geophysics at Colorado School of Mines. So this was the announcement. It was like a birth announcement in the AAPG bulletin for our department. Some people disagree with this, but it's published. The world's first Department of Geophysics. And then basically, as soon as we started this department 100 years ago, we are focusing on applied geophysics. We're taking students into the field. So on the right here, you can see a flow chart. This is actually the flow chart that governs the degree program for our rising seniors right now. Here's a similar flow chart, which you actually need to read from bottom to top. Starting freshman year all the way up to graduate studies from 1950, 75 years ago. We have 4 credits of field work right here, actually during senior year. 1950, fast forward to 2025, we have 4 credits of field camp. This has been a core part of our curriculum for at least 75 years now. If anyone has an undergraduate flow chart for the curriculum, predating World War II, that would be really cool, and I would love to see it. So this is the oldest we can find. But here I just threw up some pictures of what this has looked like through the years. So this is, I believe, Carl Hyland down here, who our seminar series is named after. He was the one who launched this department 100 years ago. This is him with someone else with an early seismometer. And this seismometer, or a replica of it, I'm actually not sure, is actually down in my lab in Green Center still. Fast forward from these kind of basic 1920s, 1930s style instruments, we start to have drill rigs out at our field camp. These are all pictures from mines, undergraduate field work. Here, if you squint, you can see a little explosive charge going off. There are some alums in the room who went to field camps where we were setting off explosives. And then here we are in the more modern days. This is probably early 90s, mid 90s, right? We're taking out our caveman computers, basically, back in the day, and we're doing some sighting to survey. We try and make sure our field camp is still kind of this style, because this is a core part of what it means to be an applied geophysicist. So we think that these field initiatives are so important that we made this the core fundraising aspect of our 100th birthday coming up next year. So if you're interested in this field camp endowment, come talk to me or Paul or Brandon. But a lot of things haven't changed with our field camp. We still go out. These are pictures from this year. We still use some old school methods. We take out our sledgehammer to create seismic sources, or we have now an automatic sledgehammer sometimes. That's Jude watching the machine do its work. But we mix in those classical methods with some of the more modern technology that you would find out in industry today. And so instead of having reams of cable all over the ground, now we have these wireless geophones that we have 1,000 of them, we go and we plant them every however many meters. You'll hear more about this. Instead of sledgehammers and explosives, I try not have explosives at my field camps. We have 60,000 pound trucks that shake the ground instead. These are kindly donated for the week by Dawson Geophysics, which we're really appreciative of. These wireless nodes are donated by an alum, Richard Degner, who's the CEO of GTI. We use modern tools too. And so on the left, you see a ground penetrating radar. On the right, you see a frequency domain electromagnetic instrument. And so we're mixing kind of the classical geophysics with what you'll go out and use when the undergrads go get their jobs in geophysical consulting or in the oil and gas world. We also really fun this year started a couple new field sites. They happen to be some of the more beautiful field sites we have, which makes them nice places to do some near surface geophysics. So this is one of our new field sites, which is a collaboration with some folks at University of California, San Diego and Colorado Mountain College, where they installed some weather stations. And they actually came to us and said, hey, we have some soil moisture probes. Is there any way to actually see if that's representative of the wider area? And I was like, you came to the right place. So we let our undergrads launch these new sites, design the surveys, start from question all the way through processing and interpretation, which you'll see today. Another new site we had this year was Stagecoach Reservoir. This is the first time we've done water-based geophysics, I think, in the history of our field camp. 75 years, we're still evolving. And so our oceanography professor, Bia, led this part of the field camp where they were going out, and you'll hear a lot about this later today. Come on. But if you're up in Steamboat Springs for the last 2 weeks of May, you'll see a whole bunch of students in yellow vests climbing all over with instruments. That's our students. We choose Steamboat Springs as our location for our field camp because it's actually a pretty exciting geoscience, geophysical destination where you talk about energy transitions, you can talk about water resources, you talk about agriculture, you can talk about water for recreation. All of these have some component of geoscience to them, and there's been almost no data collected before we were there. So this is a vast majority of the publications about Steamboat Springs over the past 150 years. Starting in 1873 was the first mapping. Cut to the late 30s, you have some folks doing some glacial extent mapping up in the Park Range, which you'll hear about a little bit from one of our groups. Fast forward again to the late 70s and early 80s, Colorado Geological Survey starts doing some work up there, trying to characterize the springs. And then kind of fast forward to now when USGS has had some small projects on and off up there. That's kind of the base that we get to work off of. And there's not much, which is really fun for our students because they get to go in, take what they've learned in the classroom, go somewhere where we don't know the answer. We also have lots of visitors because Steamboat Springs is a really great place to visit and hang out for a couple of days. And so Stephanie Tompkins, our new provost, she was up in Steamboat her first week on the job, hanging out with our students, seeing what field geophysics is all about. We also had an entire large group of visitors from the Department of Geology and Geological Engineering. After we've been in Steamboat the past 4 years, they decided to come join us for their field session. And so now we have overlapping geophysics and geology up in Steamboat, kind of broadening the questions that our students can ask. We're quickly adding to this story. We didn't know that much about Steamboat Springs before we got here. Here are just screenshots of all the titles of the projects that our undergraduates have developed themselves, start to finish. So what you'll hear today is 7 new projects that add to this set of work and then that kind of sparse set of work that's happened over the past 150 years. With that, I will hand it over to the undergrads to introduce you to the science we'll see today.
Hi, everyone. Welcome to the 2025 field camp presentations. I'm Katie Gonzalez, and I'm here with Paige and Olivia. We're going to be talking about just introducing you to what we did the past month. So we are a group of mostly rising seniors in the Department of Geophysics here at Mines. We also have a few recent graduates and some PhD students who came up to learn with us as well this year. Matt mentioned it a little bit, but Steamboat Springs is a really unique place for us to come and learn how to apply geophysics because of a few reasons, including the complex geology that surrounds the area. That's fascinating and extensive, including a hydrologic system of hot springs. We also have relatively little knowledge of the subsurface, so that gave us a really good problem-solving opportunity. And it was also a really welcoming community and a beautiful area to practice in. We spent a few days in the beginning learning the geologic context of the area. We learned about the formations from Dr. Bob, who's down in that middle picture. This is the most seismically active zone in Colorado, and it has quite a few fault systems going through it. And just like multiple layers of different formations over millions of years. And so we just got to explore that. And then we explored the hot springs that surround the area. We learned that on one side of the area, there's the Browns Park Formation and the underlying granite that caused the water to be very lacking in minerals and just where people go to enjoy the hot springs. And then on the other side, it's the Dakota sandstone that makes it that eggy kind of sulfuric smell that we got to get kind of hands-on learning experience with.
So just to talk about some engagement, we got to talk to different local landowners of the people that lived on the sites or near the sites that we are working on. And we also held a community meeting at one point as well, just to kind of talk to all the people in the area, the locals, kind of give them an idea of who we are, what we're doing, why we're doing it, and just maybe excite them about like kind of the work and what we might find out where they're living. So huge thank you to all the people that allowed us to be able to even put this field camp on. There's a lot of different people, just to point some out. We had Dawson, GTI, Collier, Earthscope, like people like that who gave us equipment and helped us out in that sense. We had people that helped with permitting, Route County, Steamboat Springs, Colorado Mountain College, Department of Transportation, State Land Board, Wildlife, the Geologic Survey, all those people like just allowing us to be there and permitting us to be able to do these surveys out there, USGS and helping us with some background geology. And then obviously Mines, the foundation, and Shell as well for just being able to help fund this so that we can go out there and learn. And then this is just an overview generally of the methods that we conducted while we were out there. There's a pretty good scope of like different methods that we use. Not all of these involved projects that we will see here today, but this is all of the different methods that we did use while we were out there. And then just real quick, there's also just some survey lines that you can see. There's some like broad or some thicker red lines up top. Those are some past surveys that we did. We did seismic up there in the past few years. And then in the kind of red zone right there, there's a dotted line. There's two different roads. That's County Road 43 and 45, which is where we did the seismic line this year, which you will hear a lot more about.
So we were permitted to work in every city park and Steamboat this year, as well as a couple county roads. So I'm just going to give a brief overview of the survey sites we were at and what surveys we performed there. So in this town of Steamboat itself, we performed a gravity survey. At Howelsen Park and Ski Hill, we performed GPR, refraction seismic, and a frequency domain electromagnetic survey. At Sulphur Cave, we performed ground penetrating radar, as well as refraction seismic. Spring Creek Dog Park, we performed ground penetrating radar. We also saw a moose, if you can kind of tell in that far image. At County Road 22, we performed a near surface seismic refraction survey with that accelerated weight drop. At County Road 45, we performed a deep seismic reflection survey, as well as a gravity survey along the same route. County Road 43, we continued that deep seismic reflection survey, as well as performed an electrical resistivity survey. At Stagecoach Reservoir, which was a new site this year, we did a conductivity, temperature, and depth survey, as well as took some measurements using that Secchi disc. Lincoln Park, we did a self-potential survey, frequency domain electromagnetics, and ground penetrating radar. And on the CMC campus itself, we installed 3 broadband stations, I believe. So we have 7 10-minute presentations for you today. We're really excited to share them with you. So thank you and enjoy.
Hello, my name is Julia Berglund.
I'm Renee Fisher.
And I'm Khadija Mariko.
We were investigating the subsurface structure of the Quarry Mountain foothills using seismic reflection imaging. We started our project with the question, what can seismic reflection data reveal about the subsurface structure, geologic formations, and fault mechanics of the Quarry Mountain foothills? We were interested in this region in particular due to the hypothesized shear zone in the area and how that interplays with fault mechanics. And so we were interested particularly in how it influences fluid migration, local seismicity, and hazard mitigation. We started with our first objective, which was mapping the subsurface structure using seismic reflection data. And from there, we were able to notice several features that brought us to the objective of analyzing the fault zones and the layers relevant to geologic processes. And then finally, once we were able to identify those, we decided to integrate our findings into geologic interpretations.
So the area of interest that we're looking at up in the figure 1 is at the northwestern part of Colorado in the Steamboat Springs area where we're located. Zooming into the image in figure 2, you'll be able to see the lines of surveys we did on County Road 45 and 43 and previous surveys done by previous field camps in the past. The geological context of Steamboat Springs is that the foundation is the Precambrian basement rock and the shear zone underlying the region. Steamboat Springs is known for the shear zone in the area. And then looking at the strata image on this side, you're able to see the layers of the Morrison, Dakota, and the Browns Park on the surface layer to show like the big environmental changes that happen in Steamboat. So then we're able to identify, hopefully, faulting fluid migrations and tectonic activities. And continuing my geological context, you're able to see here the variability in the geology and how they all coincide and work together. As the map also indicates, the black lines are the faults that are well known, and there's one big large fault going through County Road 45, and which you'll see in our data today.
Our method was seismic reflection, and so here we have a simplified model of how we conducted our survey. We have a viper-sized truck that sent an acoustic wave in the subsurface, and on our diagram, we have 2 simplistic layers on top of one another. And so when that acoustic wave meets the interface, some of those waves will be reflected because the 2 layers have different properties, such as their seismic velocity and their density. And so when those waves are reflected back to the surface, our nodes that we set up along the lines measure the movement in the vertical direction, and from there we're able to make a deduction about the subsurface structure.
So to give a little bit more context about our actual survey parameters on County Road 43 and 45, we actually were able to survey the entire length of both lines. So we ended up having 430 nodes on County Road 45 and 421 nodes on County Road 43. And we ended up keeping the same consistent spacing of 15 meters on both lines. And this was based off of previous years' want to have a little bit more spatial resolution. And to also help with this resolution, we ended up getting a generous donation from Dawson to have a 60,000-pound fiber-sized truck that we programmed to do a 16-second sweep. That was a linear upsweep from 4 to 50 hertz. And then additionally, every line has a start and a finish. So on County Road 43, we started in the west and moved east. And in County Road 45, we started in the southeast and moved to the northwest.
So just to give a little bit more background on the data processing that we did. So we initially started by getting the raw gathers, sweeps, and logs from Dawson, who actually donated the fiber-sized truck to us for our field session. And then with the help of some processors here, we were able to trim and correlate the shot gathers, as well as do some initial processing, applying geometry, noise reduction, and things like that. From there, we did some velocity analysis to start to understand what kind of velocities we were seeing in the subsurface and use that information to make root stacks and velocity stacks to see the structure.
From there, we exported it into Python and applied some transforms and filters. We used a Hilbert transform, a Sobel filter, and a bandpass filter to deduce what was noise versus what's actual structure in the subsurface. After that, we used a 3D seismic interpretation software called Petrel to make a 3D model of the dipping slab that you guys will see a little bit later in our data, and then made some velocity models of the subsurface as well. And then we created a depth migration. So all of the figures are going to be in terms of time on the y-axis, and that doesn't tell us a lot about where the structure is in the subsurface. So we migrated it to be in terms of depth, so we know exactly where those structures are, and then made an interpretation based off of that. So this is one of the depth migration profiles seen on County Road 43. On the y-axis here, we have depth in meters, and the x-axis is going to be distance across the line from west to east. You can see a pretty strong reflector that's going across dipping towards the west with those really high amplitude reflections. Circled in red here is where our group interpreted there to be some sort of structure. We can see this because the reflections are breaking up or bending, which is indicative of either faulting or folding or another geologic process. And then these annotations on the figure in red are where we interpreted there to actually be structure. And so we can see a lot of normal faults towards the east, which is pretty consistent of what we would expect in the region. And then on the west here, a fold.
So we did a very similar process on County Road 45, and you can see the very strong reflector that's moving from the southeast to the northwest. And if you look on the next, we have a couple of features that we wanted to highlight where there was breaking and folding again. And we know that there is a fault on County Road 45, so that we know is going to be closer to the northwest, which is what we have dashed. And we didn't know which side was moving which way, so we didn't want to make any interpretations about that. But we also see a more horizontal fault that we can actually see that is also normal, which is consistent with what we found on the other county road. And then we also see a fault towards the southeast, or a fold on the southeast.
So this is one of the velocity models we made for County Road 43. And one cool thing here is you can see a very similar structure to what we had for the depth migration that I showed you guys a little bit earlier. The bottom is going to be really high velocity material that's going at 4,000 to 4,500 meters per second. This is really consistent with what we'd expect of granite or any crystalline basement rock in the region. Overlaying is lower velocity material. This could be sedimentary rocks such as the Dakota or Morrison Formation that are in the region.
So on County Road 45, we were able to see a, once again, clear pattern. We're seeing that there is also a high velocity layer that is around 4,500 to 5,000 meters per second, which is still consistent with the crystalline basement rock, as well as having those layers of lower velocity material that could be sedimentary rock. So after we did this, we thought it was a good idea to make some horizon lines on Petrel. So those are the areas that there are higher amplitude things, so that we ended up highlighting them in blue. And when we saw that there was a very clear pattern. So we wanted to take a look at the other county road lines from previous seismic surveys. So we used County Road 33A, 42, and 44 in addition with our data. And we see a very similar layer, and we interpolated all of our horizon lines. And once we did that, we saw that there was a layer or area that moves from the east and dips towards the west. And when we know that the velocity of our two surveys are crystalline basement rock, and when we move towards these other ones, we know that there's well log data that shows that there is sandstone material and shales as you move towards the north.
We were able to integrate our findings into a geologic timeline. So 1.7 and 1.4 billion years ago, the Precambrian basement rock was formed, as well as the shear zones. And then 160 to 100 million years ago, these sediments are deposited on top of that Precambrian basement rock. Around 60 million years ago, the laramide orogeny occurs, which results in tilting and uplift of the strata. And then what we were particularly able to see was the 20 to 10 million years ago, extensional tectonics were reactivated in the shear zone, and that was in the form of faulting. And then concurrently and a little bit after, so 20 to 8 million years ago, the Browns Park Formation was deposited.
So the broader significance of our research is that we were able to identify that ancient crustal structures are able to be reactivated during younger tectonic events, therefore leading us to learn more and have more insight in regards to geothermal aspects of Steamboat. It's very well known for its springs and as well as the land formation over there, and also giving insight into long-term evolution of the interior western United States in regards to potential faulting in the near future. And overall, our research will gain more insight in how and gain more research in the faulting of Steamboat Springs in order to preserve its natural formation. And the future work that we hopefully we decide to do is complete seismic lines towards the east to investigate how this shear zone can influence the geological water system in Steamboat Springs in the future.
We just want to give a big shout out to a lot of people who made this project possible. We had a lot of people that were in the field in Steamboat and also helped us process the data here and made an interpretation possible. So thank you to Bob Basker, Todd Faulkner, Jim Simmons, Bob Reynolds, Maddie Pels, Aaron Gerard, and Samara Amar. These people were really critical in making this project happen. Thank you. Are there any questions?
Notice that your source sweep goes up to like 50 hertz. Can you talk about what you think the impact was on your images and what was driving that choice?
So we wanted to make sure that we would have enough depth based off of that frequency. So basically frequency determines how deep you're able to see. So we know that we're looking for very large structures that are probably going to be deep in the subsurface. So having a sweep that is large enough, going from that 4 hertz that's really low, will be indicative that we can see low enough. And then the 50 hertz, we're able to see a little bit in the near surface, just in case there's some changes, since we know that there are outcrops of, different materials, we can see those changes as well.
Time for one more question. Thank you. Right.
Good afternoon, everybody. Thank you guys so much for being here. My name is Nathan. This is Tim and Callum. I'm gonna go to this side. Today we're going to talk to you a little bit about the impact of node location uncertainty on seismic static data quality. So we just heard a little bit from the other group about seismic data generally and the kind of interpretations that can be made based on that. Well, for this presentation, we want to focus on noise in seismic data and how that impacts our interpretations. So SNR is defined as signal-to-noise ratio, and it's essentially the ratio between the signal that we're interested in seeing and the noise, which is everything else. So there's a lot of different places that noise can come from in seismic data. You have ambient noise, which comes from things interfering with our signal that we weren't expecting. There might be power lines, a car driving by, wind blowing against the geophone. You also have processing artifacts. This is when in filtering, you might have features that you are interested in get diminished, or features that you're not interested in get amplified. And then we have positioning error, which is what we'll be focusing on today. So positioning error can come from error in the GPS, and the way that you get error in the GPS depends on the method that you use. So we focus on 2 main methods for our presentation. One is internal GPS, which is built into the GTI nodes that we used, and is only accurate within a few meters. There's also real-time kinematic positioning, or RTK. This is way less time efficient because you have to go through and survey every single one of the 800 nodes separately, but it gives you accuracy within centimeters using a base station and correcting its own errors. How does this actually get applied to the seismic data? Well, whenever you have error in the XY positioning, it'll shift your signal left and right. If you have error in the Z, it shifts it up and down in time. How does this affect your interpretations? Well, just like mixing up the pieces in a puzzle, you have all the same signal there, but all of a sudden the overall picture becomes uninterpretable. In addition, you have an effect called smearing. So you see this pink color up here. It's actually composed of 2 separate colors, a purple and a yellow, but when they're overlaid over each other, the actual separation becomes indistinguishable. So the goal for our presentation today is to determine how much that smearing affects our interpretations. We have a few assumptions that we wanted to lay out. County Road 45 is pretty close to a straight line with a constant slope. We chose this to try to minimize the number of variables changing here. If you have a road with more complex topography and curvature, this may lead to more positional noise than we are addressing in this presentation. In addition, tree coverage, weather, and other obstacles may impact the internal GPS accuracy. We're also, for this presentation, focusing on quantifying the loss of large-scale features. I'll pass it off to Callum now to kind of talk about how we're going to do that.
So here you can see the distribution of the differences between our internal GPS data and the RTK GPS data. So really what we're looking at here is, do these RTK derived seismic stacks differ from these internal derived seismic stacks, and can we see this difference? So first here, I'm going to flip back and forth between the RTK and the internal, and you can see there are some very slight differences, but overall, the structure as a whole is preserved. So it's very difficult to see this just with this magnitude of error. So the next step we took here is we started adding some noise to this data. We added Gaussian noise first in our XY, later we'll see the Z. But these are processed entirely separately. So we looked at the XY by themselves first. So first we added 2.5 meter standard deviation noise and 5 meter standard deviation noise. And similarly here, you can see these are very similar. The biggest noticeable thing is there's a shift in the 5 meter. This is because the way the processing works, there are a different number of bins. So this image is basically one column shorter than the other two. So it causes a little shift. And really, you can't see a substantial change in the features just by looking at these images. There may be some effect on nuanced features, but again, generally the features are well preserved between these noise levels. So we were trying to look at a way to quantify this. If we can't see it, how can we explain this numerically? So the first thing we did is we took a simple difference between each of our cases and our RTK case. And anytime you can see a visible feature in here, like you can kind of see some of the horizontal lines in each of these from that big dipping feature in those initial stacks. That represents some place where we've lost some portion of our signal. However, these plots don't tell the whole story, because taking a certain amount of signal away from different places can have different effects. You can apply a signal which will totally wipe out a nuanced feature, but when you apply it to a strong feature like that fault, it will have absolutely negligible impact. So to kind of account for this, we adjusted this based on the signal at any given point. And there's another issue here, which is that over the scale, over our data, the variation in our noise is much smaller than the variation in our signal strength. So signal strength essentially dominates this percentage. It means that we blow up all our features around here, which is the noise where we really aren't interested in, because we had no signal to begin with. So to account for this, we applied a high pass filter to the amplitudes and filtered out, so we only kept the high amplitudes in this percent difference. And as you can see here, you definitely see the increase in signal loss as we go through here. And these are more difficult to distinguish. So we kind of tried to look at a metric here to see what's happening. So you see the mean error amplitude is generally somewhat similar between the internal and 2.5 meter standard deviation cases, but the RMS of the internal is much higher, which means that the amplitude of the errors we're seeing is much larger in this case, even if the average error is the same. And the 5 meter, as we expect, also has much higher noise, both on average and RMS than the others. And I'm gonna pass this off to Tim now.
So I'm gonna talk about a simulation result. Basically, to create figures that we just saw, we need to stack all the traces with a common midpoint together. However, in reality, not all the midpoints correspond exactly with each other. So we create bins of the size 220 by 225, and then we treat all the midpoints that falls into the same bin as one midpoint. So right now we're seeing a simulation result. We are comparing the different noise level result comparing to the RTK GPS data. We see that most of the changes occur on the two ends of the line, while at inflection points, colored by the black dot right there, there's a really minimal change as opposed to what we commonly expected. So looking at the bin folds themselves, so we see that out of 810 bins we created in the entire line, for the 2.5 meter standard deviation case, we have around 725-ish bins being changed. And for the 5 meter standard deviation case, we have around 740 bins being affected. So the bending fold changes in those 700 something bins. We see an increasing trend as we increase the level of noise in our simulation. So looking at the midpoints being reassigned, we have a total of 165,200-ish midpoints. So with the internal GPS, we have around 7,000 points being reassigned. And for the 2.5 meter standard deviation case, we have around 22,000 midpoints being reassigned. And then for the 5 meter standard deviation case, we have around 43,000 points being reassigned. So we also see an increasing trend right here with an increasing level of noise. So what if we change the Z positions? how are that gonna affect the results? So here's an example. We apply a 10-meter standard deviation on our Z axis, and we see that in the red box, there's some significant change right here. To put it another way, we see a figure that we just saw previously, and we see that there's more substantial noise change compared to the XY if we just apply noise to the Z component. And if we apply noise to all three components, X, Y, and Z, there's even a more prominent noise. Back to.
Alrighty, so what did we learn today? So in conclusion, we saw generally more loss of significant structure in the Z noise than we did in the XY noise. However, for our internal data, this was actually opposite. We saw slightly more loss of feature in the XY than we did for the Z for our internal GPS data. When we combine them all together, the XY and Z, we had the most noise. In addition, the number of midpoint bins reassigned was proportional to the standard deviation of positional error, meaning as we increase our noise, we got more midpoints reassigned and our signal shifted more. And while there was a quantifiable difference between the RTK and internal GPS data, as we were able to see at the beginning between the two stacks, there isn't a significant difference, and we don't believe this would actually impact your interpretation. So due to how time efficient the internal GPS is, that would be the recommended, broadly the recommended strategy moving on. We'd also.
Yeah, we'd like to say thank you to a few people as well. Thank you to Bob Basker, Todd Faulkner, Samara Omar, and Aaron Gerard for their help in getting this project off the ground.
Yes,
That's what we're looking for.
Now we'll take any questions. Yeah.
Let's talk about a little bit about what motivated the characteristics of your model error.
Go back. Sorry, say that one more time. Kind of hard.
What motivated the characteristics of your modeled error?
Modeled error. So are you talking about when we just the synthetic noise that we applied? So yeah. So when
Can you repeat the question for online folks?
Yeah, so she asked what motivated the characteristics for our model error, so the synthetic noise that we decided to apply. Well, we looked at the internal GPS and we actually calculated the standard deviation of it. You can see that we showed it back here at the beginning. I can get back there. Yeah, so we looked at the standard deviation we saw for our actual data, and then we decided to increase that incrementally. We also noticed that in our actual internal GPS data, the Z had more error than the XY, so we also chose to do that when we were modeling it synthetically. Good question. Thank you.
Time for one more question. There's a question online. How often, this is from Aaron Gerard, how often does the internal GPS make a record of location, and what may be a sufficient time to get an accurate internal GPS measurement?
That's a really interesting question. We didn't look into specifically like over time how our positions changed. We only looked at the final result, which it output at the end. So that's definitely something worth looking into, because basically how it works is over time it averages its position to be more accurate. So it's certainly worth considering how long it'll be out there and how that will impact the accuracy of the GPS.
All the GFOs also every couple of minutes sync themselves together in order to help better account for things like time. And I believe they're taking their own measurement every few minutes as well. It's within that, about that increment. I don't know the exact number of minutes.
DTI engineers have told me every 8 minutes I take a time sync both the converter and.
You absolutely can see, like when you're out there on the line with the tablets that we use to look at these nodes, you can see they're moving closer and kind of converging day by day as you go through. So there's definitely change over time while they're deployed.
Thank you.
Hi, my name is Olivia Wills, and together with Kaylee Doherty, Jack Logan, and Eliza Ross, we worked on identifying glacial deposits in the Yampa River Valley of Colorado. So just to give you a brief overview of what our agenda is today, I'll delve into the background context. We'll look at data acquisition and pre-processing. Jack will give an explanation of the multi-channel analysis of surface waves, and Eliza will dive into future work, conclusions, and interpretations. So our survey line was Route County Road 22, and this is located just a little bit south of two known glaciers in the area. The first one being the Fish Creek Glacier, which is around 6 kilometers to the north, and the second being the Rabbit Ears Glacier, which is around 10 kilometers to the northeast. So because there's glaciation in this region, that leads us to suspect that there was a glacier within the Walton Creek Valley. And understanding if there was glaciation in the Yampa River Valley can help us understand the valley's geomorphology and also help us identify sites for potential industrial aggregate mining. So our area investigation included many topographic features. We had a large alluvial fan, the Yampa River, and the Walton Creek. What makes this alluvial fan notable is its large size compared to Walton Creek. At Walton Creek's current flow rate, it is unlikely that this creek would have been able to deposit the size of that alluvial fan. And this leads us to suspect that this fan was in part deposited by high load glacial runoff from a glacier located further up Walton Creek. What also leads us to kind of hypothesize that there was a glacier in this region is that U-shaped valley. Rivers generally carve out V-shaped valleys, whereas glacier impacted valleys usually take on a more U-shape. This is because as glaciers form and move, they generally flow into the paths of least resistance, which is normally those V-shaped valleys. So as that glacier is flowing through that region, it's eroding more of that valley floor, taking on more of that U-shape. This leads us to kind of conclude that that U-shaped valley was potentially formed by a glacier.
Yes. So we were interested in glacial activity in the Yampa River Valley, and so we took a look at Route County Road 22. This is a map of all the data that we had access to along that road. Field Camp in 2022 went and did a deep reflection seismic line along that road and also took gravity data measurements. We did some preliminary processing on that data. We're looking at it, and the seismic reflection data was just going to take a really long time to process and look into. And so we decided for the scope of that project, we were going to just look at the refraction line that we put in place this year. So this is a close-up of that line. It was about 475 meters long, and we used 14 hertz geophones along that line. And then we used that accelerated weight drop every 15 meters until we got to about 300 meters. There was some standing water on the road, and also we kind of ran out of time surveying, so that's how far we got. But we produced 22 pretty good shot records. And so looking at that data, it was a little noisy. So as a part of our data pre-processing, we used some software that Collier Geophysics was kind enough to lend us for this project, and chose a dynamic high-pass filter depending on each of the shot records. As a general rule of thumb, this ended up cutting out frequencies above 100 hertz. And so we were looking at the data and we wanted to choose how we were going to analyze it. And originally we were going to do a refraction analysis for this refraction line. But due to the fact that the line kind of got cut short, when we were looking at this data, we saw some refractions, but they weren't really consistent along the different shot records. But what we did notice very prominently was the direct wave arrival that's marked up there, and then also all of these surface waves. And so we thought that this data would be a good candidate for MASW, which is the multi-channel analysis of surface waves. And Jack's going to talk about some of the theory of that and then our process for analyzing.
So we're going to start by talking about what a surface wave is, the SW portion of this. And surface waves are what happens when seismic waves traveling in the subsurface interact with the ground to air interface. They have motion very similar to ocean waves, where they have this rolling pattern. It's kind of a circular pattern. And as we know in geophysics, velocity generally increases with depth. So when you have these really high frequency surface waves, they're much smaller and they travel only in the lowest frequency or the lowest velocity portions of the subsurface. They travel really slow. As you get larger in the size of the wave, lower frequencies, you start reaching the higher velocity portions of the subsurface, and you get an effect called dispersion, where the lower frequencies reach your receivers first. And as you get to further offsets, this difference between the low and high frequencies gets greater, and you can learn a lot of information about the subsurface and layering based off of this information. When you do a surface wave survey, you have multiple channels. That's what the M stands for. You usually do a roll along survey. So you have a source at one location and a line of receivers. You shoot at that location and then you move the entire survey down and you go until you've surveyed everything you wanted to look at. In our case, we were initially looking at refraction. So we had a whole line of receivers and we moved our source to look at different locations. We are able to now synthesize a roll along by only grabbing a certain number of nodes adjacent to our source, which is what's highlighted in blue here. Once you grab all these all the receivers that we do actually want, we can now take a Fourier transform to get frequency out of the waves, and then you do some slant stacking to get velocity out of the arrivals, or black magic, and you get this really pretty picture that shows where the dispersion of these waves is actually happening. The brighter the colors, the more energy is happening. And here we see that our dispersive area on the bottom left is very flat, which just means that there's not a whole lot of velocity increasing with depth. We do this for every single image. So this is for our first shot record, and you pick out the highest amplitude along your dispersion curve. And this tells you how the energy is changing. And you do it again and again and again and again and again until you get to the end of your line. And then all of these correspond to a different X location. And you invert that for 2D shear wave velocity. So here's our cross section of 2D velocity getting down to about 120 meters. And then on the right side, we have our confidence map, which shows that we have really high confidence in up to about 60 meters, but it falls off very quickly. And for our purposes, we decided that 30% confidence was really good. And this is our final shear wave velocity. You can see a good amount of variability between the top and bottom. There is some increasing velocity, as you would expect in a depositional environment. And our range of velocities is from 550 to 750 meters per second. Eliza will tell you what all of that actually means.
Yeah, so like Jack was saying, we have this 2D inversion model of our velocities, and we can see pockets of both high and low velocities across the entire area. And these velocities all fall within the range of what we would expect for gravels, sands, and other like loose sediments. And what this is telling us is that we have a depositional environment of very poorly sorted sediments, which requires a lot of energy for that to occur. And a lot of energy can come from really fast, really large volumes of water running through the system. And we know that Walton Creek is not creating that depositional environment. Present day, it's not nearly high enough. There's not enough water running through the system. And it's also too close to the continental divide to like, consider larger volumes in the past. So we're ruling out Walton Creek in terms of formation of this fan feature that we see. But if we want to tie our image back to the surface, we can look at that feature right there, circled in red. It's a high velocity anomaly, maybe a deposition of higher density material or something. And it ties almost perfectly with where we see this lobe on the surface within this fan feature that we're interested in. So what that is telling us is that if the fan feature is not made by Walton Creek, and we know that there's a U-shaped valley, which indicates glacial activity in the region, as Olivia was talking about, then this fan-shaped feature we see is a glacial outwash plain, which is the first time we've identified something like this in this region of the Yampa River Valley, which is pretty interesting. And that's telling us about the Park Range glaciation during the last glacial maximum, because previously it was mapped to go a lot more north than what we see now. So we are showing that it goes further south than what was previously reported. And this is also showing us that MASW is a valuable technique to kind of investigate glacial deposits in the subsurface. So just a visual comparison between a present day glacial outwash and what we were identifying. That's in Alaska, the other one's in the Yampa River Valley. And to conclude, what we thought was an alluvial fan is not, it's a glacial outwash plain. And what that's telling us is more information about continental history, as well as an area of investigation for gravel mining or other industrial purposes. So thinking about where this project could go in the future, we are interested in getting a sediment core in the region to kind of confirm whether that was glacial deposits that we were seeing or some other cause of
stuff we were seeing in our seismic image. And we also think it would be interesting to get a date on that sediment to determine when the glacier was receding. And we also think that, like Keely was talking about, we have all this data from 2022 that was really messy and didn't fit within the 2 weeks that we had. It would be really interesting to go back and use MASW to look at that data. So this project would not have been possible without all the people up on the screen. We thank you very much. And if we have time for questions, now is a great time for that.
Dispersion image spectrum plot, there's a region to higher velocity, higher frequency that had some energy in it. Can you explain a little bit about what you on your dispersion image?
Can you repeat the question for online folks?
Keep going back.
Keep going back.
The question was why we didn't include the higher frequency, higher velocity portion. My understanding is that's more of an integer multiple that comes through with the Fourier transform than it is an actual artifact or an actual feature from the dispersion curve.
Online question from Aaron again. What do you think is causing the shear velocity to decrease with depth at 34,660 meters? The benefit of being online. You can read the numbers.
Well, because we know this was a system where there was a lot of like fans moving across and sediment getting deposited, there could be a chance that there was higher density sediment that was deposited on top of lower density sediments. This is a pretty recent deposition in terms of like geologic history.
Thank you.
Thank you.
Hi, I'm Hannah.
I'm Jack.
I'm Caitlin. And I'm Paige, and we did the imaging of Sulphur Cave and Steamboat Springs using a multiphysics approach.
So yeah, as Paige just said, we're looking at Sulphur Cave, which Steamboat. It's located on Howelsen Hill, which is a pretty popular ski hill. So it's a lot of foot traffic as well as like ski traffic. And as you can see, we're really close to downtown. So there's also been a lot of development in the area recently. So it's really important that we understand the extent of Sulphur Cave because we want to know where not to build and develop. And then furthermore, Sulphur Cave specifically is a very unique cave system because of its high levels of sulfuric gas within the cave, which makes it really toxic. And we get that from the spring source. It drains out into the travertine, and it causes this erosion that has created this cave, which is pretty unique in the first place. But also makes it really toxic for humans to go into, at least in most parts of the cave. And also is the only home to these unique like blood red worms. They're really weird looking, but they're really cool. And they're only found in Sulphur Cave. And so there's been a lot of like conservation efforts as well as like microbiology studies in this area. So that's even more important for why we want to know where the cave starts and ends, so we can learn more about the worms. But yeah, this map on the right was made, I think in 2023 by some cavers here at Mines. And so it was used last year for the field camp group that looked at the cave. And they kind of identified this unmapped extent here in the red circle. That TT stands for too tight, so it's actually too tight for the people like mapping it by hand to go through. And so it's really neat. We want to look more at mapped extent. So what we do for this is we've been looking at 2 gravity surveys that were conducted in 2022 over the area, as well as a 2024 GPR grid. And then we also use our 2025 GPR grid and our refraction line.
So just using all of that different data and just different methods that are all kind of sensitive to different properties and have different resolution at like different depths, things like that. We hope to be able to not only verify the map that has been created by the cavers, but also to hopefully be able to map that small extent that they were not able to map. And then also to suggest some future work for field camps in the future. So first method was refraction. So you can see here, we got some images of us conducting this survey. We did a survey we did hammer seismic here, and then it also was a 24 take-up cable with 2 meter spacing. You can see here, so I'll go over briefly, refraction is, we expect, depth to increase with, or velocity to increase with depth. When the hammer, we're using that as our seismic source, it's gonna send waves down into the subsurface. And then basically, these waves are gonna interact with the different layers that we see. And then when there's a higher velocity layer below, it will hit that interface and then travel along that high velocity interface for some time and then refract back up to the top. And when it refracts back up, those geophones that we have spaced out every 2 meters are receiving that information. They're able to take in the travel times, and we are able to look at what is a shot gather. I have spoiled it right here. And then you see I have some peg set right here, and that's how we determine what we think the velocities are. And then using all the velocities that we do by picking those P waves, those vertical waves, we are able to then use tomography imaging to image this. I already showed it. So this is what I was able to come up with. This is just wet refraction tomography imaging. So we have our elevation and our horizontal distance along the line. For clarification as well, might be a little confusing. There's geophone 1 to 24, and then it's flipped. It's 1 to 24 here. That's just where we had started our line. But what's really cool about this is that we see that where this little circle is, where we don't think that the cave extends, is pretty much corresponds exactly to right here where we have this geologic feature coming up. So that's really cool that we're able to verify that, as well as this area over here where we expect the cave to be. Instead of seeing what we would normally see as increasing velocities with depth, we don't see that. We see this big low velocity zone. So that's pretty cool as well. There's also some lower velocity zones than we expected in the deeper part. So it is interesting that maybe there's more below the cave than we are aware of, and that could always be something to look in the future for.
And then the second survey method we looked at was gravity. So to measure gravity, we use a gravimeter, which is shown on the bottom left. So basically you set the gravimeter on the ground, you level it, you push a button and don't move to not add any noise, and then you wait till it's done taking its reading. So gravimeters are sensitive to density contrast in the subsurface. So a more dense material will cause a higher gravity anomaly, and then a less dense material will cause a lower density anomaly. So looking at our data and the figure on the right, we had 2 gravity grids. Grid A, they're both from 2022, but grid A is from May 23rd and grid B is from the 22nd. So we would expect a lower gravity anomaly over the cave because air is less dense than the ground. And then for the grid, mostly outside of the extent of the cave, we would expect a higher anomaly because, again, the ground is more dense. Additionally, I marked it in a red circle. There is a low gravity anomaly that is outside of our mapped extent. And as Anna mentioned earlier, they were unable to map that part of the cave. So we believe that that low anomaly corresponds to that part of the cave that was unmapped.
So the last method we looked at is ground penetrating radar, or GPR. So basically we push along one of the cards that we see here, and it sends radar waves into the ground. These bounce off of interfaces and reflect back and are recorded, so we can see them in our data. It's sensitive to contrast in density, which we will see a lot of if we're over a cave. There's a big contrast between the density of rock and the air. So if we push it over a cave, we expect to see some reflections in our data. We were working with 2 data sets, one from 24 and one from 25. The 24 used 100 megahertz antenna, which we would expect to see a little finer resolution, but not quite as good depth. The 25 used a 50 megahertz, so we would see a little deeper, but not quite as good resolution. This is an example of one of the process lines from the 25 grid. And we can see we labeled a horizon on here. So we found our what we think is our cave reflection and traced manually along that. We could get a depth profile. So that's on the right there. That's basically the depth of what we expect to be our cave we observed in our data. As we can see, it lines up pretty well with our outline of the cave. For the 24 data, unfortunately, we were not able to manually map all the horizons. It wasn't clear enough in the data. So instead, we did a slice at 4 meters, which is about where we saw the roof of our cave in the 25 data. And the same thing, our reflections line up pretty well inside that outline of our cave. And as well, in the unmapped extent, see some reflections on the left and same thing on the right. So it just lends to the idea that there's likely more cave under there.
And then for conclusions and future work, for all three of our methods, we were pretty well able to see the mapped cave extent. And additionally, we verified that with gravity and GPR that there is in fact an unmapped section of the cave.
As far as future work, we would love to see a broader gravity survey that goes over the unmapped section as well as the whole map section, so we could see all that contrast. We'd also love to see another GPR survey that fully covers the unmapped extent and that uses the 50 megahertz. We found it easier to identify the cave, and also it would be ideal to have finer spacing for some better resolution.
Yeah, and then also another thing would be maybe to do another refraction line, hopefully maybe orient it in a way that we can extend the line further than what we were able to do. And maybe have the cave itself be a smaller portion of the line so that we can hopefully get some better arrivals and just be able to maybe more clearly see the outlines of the edges of the cave.
Yeah, and we would just like to thank Roy and Josh from Collier, Maddie Pels, Jeff Schrag, and John Bradford for their help with our data processing, as well as Duncan, who provided the cave map and information. Thank you. Yeah.
Is the unmapped cave extent limited to only where the 2025 GPR survey was, or do you think it extends like beyond that?
Yeah, if you go back, I mean, all of the surveys we have are very limited to the extent, like, you can kind of see in the gravity, it seems like it's probably going further. Same with the GPR, it doesn't really look like it's ending. So kind of with our future work, we would like to see the grids kind of over that area to see how far it goes.
Yeah, the density or the gravity also, it was kind of pure luck that they were located right there because that was actually before the cave was even mapped. So just going back in and maybe doing more as well, but it was kind of just pure luck that they were like right where that little spot was.
What are your thoughts on the velocity model from the refraction survey?
Yeah.
Where in the locations that you see the velocity decreases with depth.
Yeah, here, I'll go back. This, yeah, so I was pretty confident in, some of this, like especially that like high velocity zone, pretty much corresponded exactly with what we would expect, not only on the map, but in person when we were actually putting the geophones in the ground. It felt like we were trying to put them into straight travertine at that point. So that like made a lot of sense, as well as even the general like low zones right here. We also know that the cave is around 5 to 6 meters of depth. So this part like we're pretty confident in. Something that's interesting, and I'm not really sure, like didn't go too much into the interpretations about, is these low zones. To be honest, these ones down here, I'm not 100% confident in, but in multiple inversions that I did run, there was still this little stretch that kind of like would bend here. So it definitely would be interesting. And I think that's why like going back with another refraction survey could be interesting to see if that's still there in other data. But as far as that goes, I think just having maybe some potential, like I guess maybe extensions of the cave that they're unaware of could be present, but.
Thank you.
All right, good afternoon, everybody. My name is Lucas. I'm Ian. And I'm Nate. And our field camp project is looking at Howelsen Hill as well, this time trying to identify some causes of the landslides and slump failures that have been occurring on the hill using frequency domain electromagnetics. So first of all, go into a little bit of background information about our site. Howelsen Hill, you can see looking up the slope over here. This is a city run ski area, but it's had a lot of slope failures, a lot of landslides in the past, and you can see those be like stuff like this. Some newer events, and even over here, this grass covered patch is actually an older slump. So this has been going on for a while, especially during the spring seasons when there's a lot of precipitation, meltwater. But it leads us to some interesting questions on like what causes these landslides, and more specifically, if we can use FDEM data to identify the causes of these. So for a bit of geologic context, first of all, surface geology map. We have downtown Steamboat kind of over here, and we were right across the river over here. So we surveyed right on top of the Browns Park formation on Howelsen Hill. And what that looks like on the hill is some poorly sorted sedimentary rock. It leads to a loose topsoil layer. And then below that, you'll find a more well-consolidated layer that's a bit more clay-based. And then actually right down to the southeast, we have this pretty cool travertine layer composed mainly of limestone. And then now to get into a bit of our method, frequency domain electromagnetics, or FDEM. This is a great way to apply this method. The main property that it's sensitive to is electrical conductivity in this case, although there are other properties that it's sensitive to as well. So this means that it's good for identifying water, metals, stuff like that. And then FDEM also looks through a range of frequencies. Low frequencies giving you more depth at less resolution, high frequencies giving you less depth at more resolution. So you can kind of do like depth soundings with FDEM. Here's a little bit about how this method works. Our instrument is the GEM2, which is this like kind of gray piece right here. But the GEM2 has a transmitter and a receiver at fixed positions. The transmitter emits an electromagnetic field, and then things in the subsurface, like what you'll see in future slides, will have a response to that, an induced electromagnetic field that the receiver can then pick up. Here are actually a few pictures of the survey crew, which Ian was a part of. They attached it to the GPR cart, and we're kind of carrying it or walking it around the hill in different lines, leading to some interesting terrain challenges that Ian can now talk about.
Yeah, so before we get into the actual results of our survey, it's important to know where we are. So in the top left corner or right corner, you can see that red mark is our survey grid over satellite imagery of Howelsen Hill. So we're right about 100 meters up from the baseball fields and the rodeo that is next to the Yampa River. So with that in mind, we took LiDAR data provided by Gabe Walton and Routt County to produce a 2D and 3D map of where our survey grid lies. So oriented north on the left is our 2D grid, and you can see that the grid was taken in a bunch of lines. We actually did one solid line, but we went back and forth, and that is descending down the mountain. And then the 3D grid or 3D plot on the right is the survey grid. Now look with the hill pointing towards you guys in the audience. And that's the survey grid look. So for a quick frequency comparison, GEM2 produces raw data in ppm, parts per million. And we wanted to show you guys a comparison between the frequency data and raw outputs. So for 450 hertz, like Lucas said, it is low resolution, high depth, and whereas 63,000 hertz is high resolution, low depth. And you can see clearly in the 63,000 hertz data that there's some interpretable anomalies in the subsurface, whereas in the 450 hertz data, that is clearly not evident. So with that in mind, we were able to calculate the apparent conductivity. And then with that, we created a layered plot of the different frequencies. So at the top, we put 63,000 hertz descending down to the bottom layer at 450 hertz. And we did this way because 63,000 hertz in the high frequencies are close to the surface, and the low frequencies are lower to the surface or farther down in the surface. So you can see as you go down that the anomalies appear less, it becomes more ambiguous, the anomalies as you go down. And the 450 hertz data is clearly a lot more noisy and harder to interpret. So for processing measures with that in mind, we decided to remove the turning points that we took because that introduces a lot of noise in the GEM2 data. And then after that, we applied a high and low pass filter. So we went from apparent conductivity being up to 1500 down to about 1000. We determined those points were somewhat erroneous and noisy, so we got rid of that. And then we also got rid of some of the low conductivities on the left side of the data that appeared more out of the norm. And then we also took every fifth measurement instead of every measurement because the GEM2, we got about 57,000 points measured at about every couple of milliseconds, which was, for a diffuse emissive, there was no need for that many points, and it made things harder to interpret inversion-wise. So we got rid of that and did every fifth measurement to lead to faster interpretations and hopefully less noise in the data.
Alrighty, so before we can get into talk about our results, unfortunately, we need to talk about that 450 hertz data. So here are slices from two different inversions. The one on the left used everything but the 450, and the one on the right used everything. Orientation wise, uphill is down to the left, towards the parking lot is up to the right. We'll talk about that left figure a lot more in a little bit, but the main thing to see is that we have some clear structuring here. When we go over to 450 and use that, we lose all structuring. And colors wise, what that's showing us with 450 hertz is all those blue areas are incredibly conductive. And then all the white areas are where the inversion actually produced negative conductivities, which of course aren't possible. This is just a 3D view of that inversion from the last slide with the 450 hertz data exempted. This goes down to 10 meters deep and we used 0.1 meter thick layers. And now uphill is kind of off to the left and into the board a little bit. For color maps on this, the greens and yellows are less conductive, while the blues more conductive. And we have a couple interesting things to point out here. First off, we have this very clear T-shaped anomaly, which we have overall decided is likely something human in origin, just because of how cohesive it is. And we can also see we have our little slumps here, and those both have high conductivity anomalies associated with them. We can also see that the uppermost layer is a lot less homogeneous and very conductive, while the lower layer is a lot less conductive. These are just two depth slices from that inversion at 0.5 and 1.5 meters deep. The first thing to point out is we once again see that T-shaped anomaly very clearly at 0.5 meters deep. It's mostly gone by 1.5 meters deep, so we think that that is roughly the maximum extent of that feature. And then also that highly conductive, inhomogeneous stuff at 0.5 meters deep, we believe is the topsoil layer, which is poorly sorted, not very cohesive, and also very spatially varying in its water saturation. And then we think that at about 1.5 meters deep, we transfer down into the clay layer, which is a lot more cohesive and contains a lot less water. Overall interpretation, over on the right, we have a utilities map of Howelsen Hill that was provided to us by Steamboat Parks and Rec. That square on that map is where we surveyed, and it's a bit hard to see, but we have a line coming there and there. Those are actually snowmaking pipes that were put in at Howelsen. We did not know these were there beforehand, but it helps to explain that T-shaped figure. And that is also interesting because we can see that these little slumps are about even distances from the junction in that pipe, which leads us to believe that there may be some association between that pipe and slumping. And also from talking with Parks and Rec, we learned that the pipe is a iron pipe with a concrete lining, which helps to explain that anomaly we see with the highly resistive center and conductive on the outside. And then we also find that the topsoil is highly water saturated, especially near those slump areas, which makes sense as water saturation is a main driver of slumping activities.
Awesome. So all in all, there are a few key takeaways we can get from our data. First of all, that highly saturated topsoil layer that appears more conductive in our inversion could be a cause of some of the slumps and landslides we see, especially if that loose layer starts breaking off the more well-consolidated layer below. So that's one potential cause that we identified. And then, as Nate also mentioned, the snowmaking pipe with the slumps associated with, that's a little interesting too, and that could maybe be another cause of some of these slumps. So I think in the future, it would be really interesting to check out some of the other pipes on Howelsen Hill and see if there are slumps associated with those as well. But overall, we believe that these results could be pretty important for informing future mitigation strategies with these landslides, especially in more targeted areas than we've seen previously. But yeah, these are our conclusions. And we'd lastly like to acknowledge a few people who made this project possible and gave us a lot of assistance. So Dr. Joe Capriotti from the Geophysics department provided a lot of insights, especially with inversions, interpretations on various processing steps along the way. Dr. Gabe Walton and the geology field camp students provided us that LiDAR scan that Ian used for the point cloud that we showed earlier. And then we'd also like to thank Brad Setter from Steamboat Parks and Recreation, who provided the utility map, as well as confirming the material of the pipe that we saw. So thank you to all these people, as well as thank you for everyone else who took those data and gave us assistance along the way. But that's what we've got for you guys. If you have any questions, feel free to ask, and we'd love to talk about our project more.
Dr. Gabe Walton asks, could you please elaborate on the potential connection between the snowmaking pipes and the slope instability?
So I'll go back. So far, we're mostly at a correlation result. We see that there is some association. We don't really know enough to explain why that association is there, though something like a leak could definitely explain this.
Any other questions?
So let's say you think it might be a leak and you want to give advice to field camp students next year about what data to collect. Do you have any suggestions about how they might differentiate if that's the mechanism?
Yeah, so maybe like doing some sort of soil moisture survey and seeing how the soil moisture content changes right next to the pipe versus farther away from the pipe, because that could indicate maybe some leaking water out of the pipe. And that would be a very localized survey though.
So it's my understanding that there are also a lot of drainage pipes on Howelsen Hill. Do you have an idea of if the same phenomenon could be connected to those drainage pipes as to the snowmaking pipes?
Not as of yet, just due to the fact that this is the only region we surveyed. It would be a great idea to investigate that in the future though.
One more online question. Knowing that they recently replaced the lift towers at Howelsen Hill, what would be your suggestion to monitor or mitigate these issues in the future?
It's a great question. I would definitely recommend, like, as Ian said, trying to investigate more of the soil moisture and like seeing if like what we identified as potential causes are actually true, because especially with things like the pipes, and since this is just like one kind of small area on the hill, we don't really have a great enough sample size like over the hill to really determine that this is the cause, because these happen at different places over the hill. So we don't have the spatial coverage right now, but I think it would be good to look at kind of more areas and see if that's actually true.
Yeah, I think it could also be interesting to maybe mark a known point and see how over years it's changing. So you can kind of see the slope movement in itself, because I'm sure even though there's slumps, I'm sure the rest of the slope is slowly moving downhill as well.
Thank you. Gotta move on.
Hello, I'm Finley.
I'm Jude.
And I'm Katie, and our project is, we're all rising seniors in the geophysics department, and our project is on the spatial variability of the water in Stagecoach Reservoir. So this was a really exciting year. It was our first time being able to do lake geophysics at field camp, thanks to a few dedicated instructors. We were really excited to look at the reservoir because the lake dynamics showed us a lot of information about this lake in particular, Stagecoach is vulnerable to harmful algal blooms that are unexpected. And doing all this studying and being able to understand it can give us insight into how organisms and nutrients move, the likelihood of a possible algal bloom, and it also tells us where where boats can travel and where people can swim safely. So the system in this lake is predominantly controlled by circulation. The circulation of the water, in turn, is controlled by broadly describes the way that the water behaves when there is differences in density over space. So if you look at that picture, we have kind of a middle school science experiment, but this density depends on a couple of factors, including the temperature of the water and the solutes that are dissolved in it. So this lake is not an isolated system. These influences on temperature and solutes come from lots of different places. When we think about temperature, the sun is a big driver. It warms up the shallow parts of the lake and the surface parts. And the inflows and outflows of the lake, there are a few creeks and one big river coming through the lake. And that can cause fresh snow melt to reduce the overall temperature of the lake. There's also wind mixing that will kind of, create a middle ground between these two. When it comes to solutes, there's a lot of agricultural and quarrying activity in the area. So runoff from those processes can make its way into the lake. And then geologic weathering of the rocks adjacent to the inlets can also add solutes. So we wanted the instruments that we use on the lake are designed for ocean water, but we have a wildly different range of specific conductances, which is a proxy for how much solute there is in the water. It can be 58,000 microsiemens per centimeter in the ocean, where we have a range validated by our data between 430 and 450. So we wanted to understand whether or not conductivity was actually influencing density. So when we plotted it, you pick a temperature and you can see that the effect of specific conductance or a change in the solutes is basically negligible for the density. Therefore, moving on, we've absorbed that temperature is the dominant control on density in this situation.
So our question was, how do inlet fed coves and non-inlet fed coves, spatial and vertical temperature structure vary in the Stagecoach reservoir? So to collect all the data out on Stagecoach, we use the Castaway CTD that you can see on the left here. It's got 3 sensors in there, and as it's getting dropped into the water column and pulled back up, the water flows through that flow-through cell, and the 3 sensors measure the temperature, conductivity, and pressure. The CTD derives the depth from the pressure. The specific conductance, salinity, density, and sound velocity are also derived by the CTD. And then here we can see our 2 survey locations. The red is Keystone Cove, a cove with no inlet. And then Harding Cove is in the blue, which is a cove with 2 inlets. There's one up on this end, one over here that we'll be looking at. Now, in total, we collected 166 measurements across the reservoir that were valid, and a few others that weren't.
So the first thing that we did when we got our hands on our data was plot Keystone Cove on the 18th of May and Harding Cove on the 17th of May, of their conductivities versus their temperatures. You can see that there's a pretty clear linear relationship between Keystone Cove's properties, whereas Harding Cove has a much more variable non-linear pattern. This may not tell us much about the circulation patterns, but it does tell us about the different conditions that each cove is in. But moving forward, we will focus on temperature and its influence on density and circulation.
So looking at temperature, we're looking at the Harding and Keystone Cove. here's all the measurement locations we had, for a single day at Harding Cove. Same with Keystone. The red line is the transect that is shown on the right. But we decided to leave out a few of the points on Harding Cove, because initially we had them all. But those points, since they were close to the shore, were skewing the plot. And then when we're looking at the transects, the main thing you want to take away is that Keystone Cove, the one with no inlet, is very layered, stratified. Whereas Harding, you see it starts out cool, kind of rapidly increases, and then it's pretty well mixed. Zooming in on Harding Cove, we've got plots of the temperature at specific depths. So we start shallow, move to a deeper depth. When it's shallow, you can see over by the inlet, it's generally cooler, as well as with this inlet here. But the temperature does vary a lot. And once you get down to about 1.35 meters, it becomes pretty uniform. And then looking at the transect, you can see a few of these warm pockets, but that cold water is kind of seeping down under and helping mix the cove. Whereas with Keystone, it is generally pretty uniform in temperature at each of these depth profiles. And that's also verified by the transect here, where we saw it was very layered.
If you want to learn more about our work and get a better look at it, we have made a website. It's not fully finished yet, but you can access it. It should be finished in the next couple of days. Here you can find information on our project in whole. We have sections on the background, data collection, and results of our project. And we also have included the code for our project, so you can look and either reproduce our figures or make your own, depending on what you want to do. And then also in the works is an interactive map. And this should be done soon. I can get the video going. And this includes every single measurement that we took, and it will give you what test type it was, the date, the file name, as well as the location, whether it was in a cove, inlet, or dock or middle of the lake. And then you can also look at profiles of temperature, conductivity, salinity, and density, and pull them up in different windows. So yeah, if you guys want to visit that, you can scan the QR code or visit the URL. Should be up and running. And I gotta get this going again. Okay, but what can we conclude? Like Katie said, freshwater circulation is driven by density, which is dependent on temperature, which is why we focused on temperature and then analyzing the coves with an inlet and without an inlet. And we found that inlet-fed Harding Cove was better mixed with cooler surface temperatures near the two inlets that we found, whereas the non-inlet fed Keystone Cove was stratified with warmer profiles in general. So for future work, we want to work with the geology department during their field session to conduct geochemical samples at both inlet and non-inlet fed coves to understand what sort of nutrients are in the water, and then develop a structure for surveying these areas daily. So that way we can assess how they're changing both temporally and spatially. And then potentially setting up a portable weather station to get time-lapse weather data to compare the weather conditions with the properties of the water that we're seeing. And then also just updating the website to track the types of data we're collecting it, why we're collecting it, as well as how, so that way future groups can continue to see what we're doing, and as well as just everyone can see what we're doing at the Stagecoach Reservoir. So thank you. We have some acknowledgements, but we recognize that we don't have a lot of time for questions, so we're going to open it up for questions.
Can you go back to that figure where you showed like a transect, and then you had like a profile? Yeah, this one's fine. So we have casts at like specific locations. How did you get this like 2D?
So I took actually, if we go to the one before, there was this transect here, projected all of the points onto that transect and use the SciPy interpolate function to interpolate it over.
Yes, Ryan?
You mentioned being interested in geochemical measurements. Which ones do you think you would like to measure?
That is something we haven't really researched extensively yet, but probably just like pH, other geochemical. Geochemical, not my expertise, so,
We'll help you.
yeah, we need it.
Also, when we were trying to look at the equation of state, calculate the density for the fresh water. It would be nice to know what kind of particles are suspended in the water. That way we could get a better estimate of the density.
Yeah, we guessed on the coefficient for the equation. Yes, Matt?
Question online from Eric P. Was this data presented to CPW, which I don't know what that stands for? And what do you think they will practically use this for? Like, is there a way to predict the location or severity of algal blooms? This is a big issue for Stagecoach.
Colorado Parks.
Yeah, we haven't talked to Colorado Parks and Wildlife about it yet, other than just the time we met a ranger in the visitor center. They seem really excited about it. We know that the Yampa has a water conservatory group that or conservation group that could definitely like this data. We would, right now, since it's such a simple set of measurements, we're not sure what we could help them derive about the algal blooms, just that we know that we're on our way to figuring something out. And if they wanted to collaborate in the future, we'd love that.
Thank you.
All right, hello everyone. This is our project on how temperature influences mixing dynamics of Stagecoach Reservoir. My name's Jimena.
I'm Seth.
I'm Mariana. Okay, so I'm gonna repeat a lot about what the parent group said. We did our project also at Stagecoach Reservoir near Steamboat Springs. It's super excited because we are the first geophysics field camp to be able to study in this lake and be the first ones to kind of start to understand the lake mechanics and dynamics of the reservoir mixing at Stagecoach, because no one's ever really studied it before. And like the prior group said, this reservoir is prone to harmful algal bloom events that shut down the entire lake because we don't really understand where they are at Stagecoach. And so we want to kind of help Stagecoach Reservoir understand why.
There's an alien here. No, don't know where that came from.
Okay, we want to help Stagecoach Reservoir understand like why and where these harmful algal blooms happen. So a little bit of background on lake mixing and what drives these algae blooms. They love warm water, especially at like the surface. And so we're kind of thinking about the lake and the stratification of layers and where warm water sits at the top of it. And lake mixing is where you're gonna get this from, and that is mostly driven by weather. So when you have like a temperature difference in the atmosphere versus the water, and the sun is like warming the lake, that's gonna introduce maybe some algal blooms. And also let's say you have wind and there's turbulence in the lake, and that's kind of bringing up the upwelling of nutrients that algae really loves. That could also cause it. And also just to give you an idea of what the data we're going to show you looks like. Over here on the right, we have this red line that is what our lake profiles are going to look like. So we define that mixed layer as like homogeneous stuff, uniform temperature,
going into that transition layer or the thermocline, and then down into deep water, which is generally cooler temperatures. So we are only looking at the data that was taken at the boat dock of the reservoir. And now we're gonna walk you through how the weather influences the mixing here at Stagecoach.
Okay, so a little bit of review again, but when we were in Steamboat, each day that we were there, a group went out to the reservoir and took CTD measurements out on the dock, also known as conductivity, temperature, and depth. As Finn talked about, this basically works by attaching a weight to the bottom of the CTD, letting it free fall through the water, and then there's a tube that the water runs through, and measurements are taken about the water property. Depth profiles that we got from this data collection, and ultimately trying to connect changes in these profiles to local weather. So our first big question was, how do the CTD profiles vary over time? Here's a plot that shows these CTD profiles from each day that we were out on the reservoir, with each color corresponding to one of the locations on the dock that we were sampling. And so on Y, we have depth going down to about 9 meters, and then on X, we have temperature going from about 8 to 13 degrees. And right off the bat, it's pretty obvious that there is a lot of change happening in these profiles over time. If you look at the May 13th on the top left, you can see the mixed layer depth is at about 5 meters deep, and it's pretty similar for each dock location. But then even just over the course of 24 hours, if you look at May 14th, you can see that the mixed layer depth has become a lot more shallow, closer to like 2 meters. And you can also see variation between each dock location, especially in the surface temperature at the top.
So in taking the MLD, it can be kind of difficult because the trends themselves, and even though like the forces that affect them are the same, they can be displayed differently throughout the day. And so just trying to find something consistent through all the profiles was kind of important. So I tried to do a second derivative pick. So I looked at the second derivative and found like the peak of it to find where the rate of change was greatest. And that helped me to better constrain it across the entire profile at the dock. So to better, because our temporal resolution was just kind of once a day, I tried to model out a 1D heat equation using the Craig-Nicholson, basically so that I could simulate for extended time periods. What we found from this though is that by roughly like 300 minutes or 6 hours, it had reached a steady state. And that kind of led us to confirm that our frequency of sampling wasn't fine enough. And so we can't capture a lot of these more frequent or periodic features. And that we'll need to look at that in the future.
Using those mixed layer depths that Tom found, I was able to associate each cast with a distinct depth point for an assumed mixed layer depth. That was represented in this animation here as it expands temporally over those 7 days. It's separated by dock, where we have a western, central, and eastern dock. And for context, these are roughly 35 meters apart. What I find really interesting is how variable these profiles vary vertically. Between the west and eastern point, there could be anywhere from 5 meters in difference between those points, which shows how significantly not only the vertical but horizontal heterogeneity is between these dock locations. This is similarly shown in the temperature profiles, where not as prominent as the mixed layer depth variations, but between each of these dock locations, we can see, distances short of, as say from me to Roslyn away, we can see a full degree in Celsius difference in these short areas. This horizontal heterogeneity aligns with some of the research that I've seen in limnological studies regarding the mixed layer. And it really just kind of shows how important it is to further understand how this varies, not only spatially, but temporally as well over time, to really lay the groundwork for future studies in regard to those submerged blooms.
So our next big question was, how does local weather influence these temperature depth profiles over time? We did this by looking at weather stations that are a part of the CW3E project out of UCSD. And our original goal was to look at how wind influences mixing, but we pretty quickly realized that because wind is so variable across the region, we wouldn't be able to pull wind data from a weather station that was like for example, 7 kilometers south of Stagecoach. So that's kind of justified by this plot on the left. This is 2 stations that are adjacent. They're about 20 kilometers apart. And you can see that there really is very little correlation in their wind speeds, which basically justified to us that we can't use wind data from this C3 SKI station near Stagecoach. However, we did have more success looking at air temperature records. You can see that there's much more correlation in air temperature across the region, and that told us that it would be a safe bet to use air temperature records from the C3 SKI station to assume air temperature at Stagecoach.
And to kind of further verify some of these gaps in weather that Mariano was discussing, I went ahead and attempted to plot the mixed layer depths against various information from the local weather stations, such as wind, ambient temperatures, as well as precipitation, and I couldn't find anything notable manually or statistically using various Python packages, being that we don't have enough data or robust enough weather data close to the lake itself. But we were able to find that the ambient temperatures did have some mild correlation with the mixed layer temperature itself, rather than the depth. And you can see that notably it was warm prior to our measurements on the 13th, and then during our measurement midday on the 13th, we saw a major drop in about 15 degrees between the 13th and the 14th, where there was a roughly 2-degree drop in the mixed layer temperature. It remained relatively stagnant after that, with some mild spikes into the 17th and 18th in the westernmost dock location. So it really just shows that these ambient temperatures do have some effect on the mixed layer temperatures overall.
So for future recommendations, it's really just building a more complete and robust time series. We recommend going to the southwest and making that a new control station, because there is a NOAA river surge station there, so you can better control and understand how water is coming in and out, and use that to better improve our models. To take wind and temperature readings during our CTD measurements, so that we can better couple weather mechanics to our lake observations. Oh, and then also to do geosampling or partner with geologists as well for the soil and water mechanics, just to better understand how those might change and how that might impact algal blooms in the future. And then in conclusion, we collected and analyzed profiles at Stagecoach for the first time at field camp. We identified that there is a temporal and spatial variation, and then we were able to observe some coupling between the mixed layer and the ambient temperature, and then constraints for how just temperature changes without anything else. Special shout out to Bia and Colin. You guys helped a lot with bringing in our understanding and kind of how to present and our storyboard. Thank you. And then, is there any questions?
Right.
I would think maybe, yeah. I think one of the things that I observed that we didn't put up here is that the bottom temperature changes quite frequently just through these 7 days. And so I would think that the water goes beyond just the depth of the basin. And so just to see how maybe the groundwater that we can't quite observe with the CTD, where that extends to, might be interesting and help to better inform where the water is coming from.
Question online from Jackson. Do you have any recommendations on getting accurate wind data to analyze with the CTD data?
Yeah, I think our idea with the wind data problem is, I don't know exactly the most efficient way to do this, but some kind of weather station, or if we often had to split in 2 groups, with one being on the dock and one being on the shore. So if the group on the shore could take hourly wind measurements. I'm not sure exactly what equipment looks like for that, but I think that would be much more helpful to sort of quantify the influence of wind on mixing in an accurate way.
Thank you. So that was our last student presentation. Now Julia and Jimena here will wrap things up and do a slightly broader Q&A for our last 15 minutes to answer any questions you might have about field camp as a whole.
Yeah, so again, thank you everyone for coming. We hope that from these presentations and all these projects that we worked on, that you see how much we learned at our Mines Geophysics Field Camp experience and how we were able to apply all that theory that we've learned in our geophysics classes to these real world problems. It was incredibly valuable to be working out in Steamboat in these different environments and not just on like the ideal flat grasses of Capadar. We love Steamboat. We really appreciated working with the community and answering their questions and concerns, as well as just sharing the excitement about the science that we did with them. This is also just an incredible professional development opportunity for all of us in the class. I think we all feel better equipped to take on the next geophysical project that we work on, especially on the fieldwork side. We worked so hard on that and we learned so much as well.
So once again, we just want to give a big shout out to everyone that made this possible. This is a really big undertaking for not only the department, but everyone that's involved. So thank you to everyone who helped fund and everyone who donated time or expertise. It was such a great opportunity to be out there and learn everything. So thank you. And with that, we want to open the floor to any questions about specific projects or just anything about field camp in general. Yeah.
I didn't realize that you had the 60,000 pound dive this year.
No, I don't know that when I talked to Steve inside the Viper size truck.
Who's Steve?
Steve is the operator of the Viper size truck. And so in past years, it sounds like they had something around a 16,000 pound Viper size truck. And students were able to drive that in Pagosa Springs in previous years, but it doesn't sound like anyone's actually driven it in Steamboat Springs, to my knowledge.
I think it's an insurance problem. So I have a question online. I'm not going to say whose parent this is. I have a question not related to the students' findings. I'm a geophys student's parent and want to know what drives the students to do this research.
Interesting. I think aside from it being a course requirement, and I think we're all really interested in earth sciences, and geophysics is so cool because it's such a broad science. Like we have people that are interested in like volcanoes and glaciers and subsurface faults. Like I think that you could do like a lot of different earth science fields with geophysics, and so I think we all have that passion and that drive to go out and learn about what's underneath.
Yeah, and just to add on to what Jimena was saying, I think for me, and I know I'm speaking on behalf of a lot of the other students, it's just such a big curiosity about the natural world, and understanding the dynamics that are actually driving that is something that really inspires me to do this kind of research. Katie, and then in the back.
I was just gonna ask what the most impactful interaction you had with a community member was.
Okay. Okay, so I know a lot of the students here know a little bit about the story about stuff on the reflection line, but we were putting in nodes on a county road in Steamboat Springs, and there was a rancher there who was very concerned about impacts on his surface water. He had told us that there's a lot of fighting back and forth with the state and the county about his water rights. And so he was concerned that the investigation we were doing was going to impact his access to water. He also had a $37,000 peacock. 36,000, I don't know.
I'll buy him a peacock.
Yeah, very expensive peacock, and he was worried that the work we were gonna do was gonna disrupt his peacock because it sounded like that's a decent source of his income. And so I actually got to talk to him with Paul Sava, and it was really impactful for me to understand, you know, the work, when we go out there and we're doing this kind of work, it's our scope is like limited into the science. And so we're seeing, you know, we want to get from the experiment to collecting the data, but we don't necessarily think about how that's impacting the people in the process. And so being able to talk to him for me was really impactful to see that connection to how are people being affected by the work, and, you know, how can we communicate effectively
in that sense. So that was really impactful for me. And then in the back, yes.
Yeah, it's just a great question and congrats on the presentations. I was wondering to what extent the Colorado Geological Survey, the US Geological Survey have had sort of direct engagement in the field programs, and are there opportunities in the future to further leverage that partnership?
Yeah, well, first of all, thank you. And we do have like some USGS data in Steamboat Springs, but these projects, I mean, they're very real and like they can lead to our senior design projects and maybe collaborations with USGS. I know like a lot of the geophysics department hopes to work for them one day. So definitely like expanding that partnership would be great in like future field camps.
Seth, would you like to add anything to this?
Yes, thank you. My name is Sittin. I've been helping teach field camp for 15 years or something, maybe more than that. This year, that was not allowed thanks to our current policies and travel bans and whatnot. Hopefully that'll change. Nonetheless, I remain very supportive. I think it's awesome. So glad to be here today and also glad to talk with any students who may be interested in USGSE questions. Spoiler alert though, we are definitely not hiring right now.
So we've historically had 2 or 3 USGS scientists come out and help teach field camp. Seth was one of our longest continuously teaching instructors at field camp, predates me by many, many years. And so this was the first year he had to take off because of the current situation in the federal government. And so that was a big bummer for these students. They're the ones who lose out when the federal government makes decisions like this. We've also had CGS seismologists come out. CGS was working with the geology field camp a bit this year. And so we also think that the integration of geology and geophysics field camps will help support even more engagement from these external partners. But the external partners we had this year were amazing. Collier Geophysics filled in a lot of holes we had and came out. And so we really appreciate that. And our industry partners are still supporting us very strongly. We have the CEO of Dawson Geophysics on the Zoom today, so that's pretty impressive. Any more questions?
Yeah, sure.
What would be your recommendation for the next class coming out of units?
Just like,
as far as, you know, what should they key in on in their classes? What should they take going to geophysics or to field camp? What should they get out of field camp?
I mean, I personally think, you know, the sequence of Applied Geophysics 1 and Applied Geophysics 2 is really crucial going into this, because we started to learn, you know, what the methods are and how we use them and what physical properties they're sensitive to. So being able to go out there with a clear objective of, hey, we want to survey this, what method should we be using is really important.
I agree that like the applied geophysics classes are extremely helpful leading into field camp. I think my one piece of advice would be write detailed notes in your field notebook and apply geophysics so you feel better prepared when you're writing your field notebook in field camp. I mean, it felt like once I was in field camp, it felt like second nature to write like my name and the date at the top of every page, and obviously more important things that come from that, but it's just like an essential thing, a big part of your grade too. Yeah.
So I'm gonna cut in and cut off the Q&A. I'm gonna put on my Paul Sava hat. Usually he comes up here and gives this little speech at the end. Thank you. Paul's in France, so he can't be here. He's at a conference. But the first thing he always does when he comes up here is talk about how completely insane what you just saw was, right? This field camp started less than 4 weeks ago, 3.5 weeks ago. And so they went through the entire data, experimental design, data collection, data cleaning, data processing, data interpretation, and preparing a presentation in that amount of time. We got back and they got their project assignments the day after Memorial Day. And so to fit this amount of science in what, 7.5 days is incredibly impressive. So thank you, students, for putting up with a really intense field camp. we can't put this on unless everyone else in the room is supportive of this. Field camps, geoscience field camps across the country are disappearing every year. And we're pretty much the last single university land-based geophysics field camp in existence right now. The only comparable field camp is put on by a consortia of universities. And so we obviously feel really passionately that we need to put in the effort and keep this up. But it's really inspiring to see the vice president of research, to see the CFO of the university online, not in person, to see that sort of support. So thank you from the top of minds down to the bottom of minds, the people who sign off on permits, the people who do all of the insane number of purchases we need to make this field camp happen. We overrun maps this time of year. Thank you to Rachel Plotz, who's our new department manager. Can't do this without you, or our instrument technician, Brian. And it's just dozens and dozens of people who make this happen every year. So thank you all. Thank you for listening taking 2 hours out of your day and listening to us drone on about the interesting geoscience to do in field camp. And we hope next year we have a little bit more participation from geology in these sorts of presentations. Don't forget, we have a barbecue tomorrow at noon. Everyone here is invited. Please come eat our free food. And we might move it indoors. We haven't made that call yet, so stay tuned. We'll put up a sign somewhere so you know where to go. And have a great rest of your Thursday.